back. Today we're going to explore what is known as linear operators and linear transformations and also linear functions and talk about what they actually represent and why they may be useful in the study of vector spaces. So first off, what exactly is a linear function? So in terms of this conversation, the words linear function, linear operator, and linear transform are going to be synonymous for most of the time. So we say that a function is said to be linear on a set S if for all x and y in S and scalar C in some say scalar field F, the following properties hold. In some sense, F can distribute over the sum of two objects. So for example, if S is a vector space, F pretty much transforms the sum of two vectors into the sum of two new vectors, Fx and Fy, and scalar multiplication can sort of factor out outside of the functional. So some people will actually bring these two properties into the same property and write f of ax plus by is equal to a f of x plus b f of y. Right? So let's just make sure we understand what we're talking about here in the sense from vector spaces. So let's assume that S is a vector space and X and Y belong to it. So this is scalar multiplication inside of S, this is scalar multiplication inside of X, and this is vector addition inside of S. But notice that here we have a function f which maps S to another set T, and T could possibly be a vector space as well. But notice that f of x belongs to T, not S, and f of y also belongs to T and not S. And this is scalar multiplication in T, this is scalar multiplication in T, and this is vector addition in T, right? So although I'm using the same notation for the plus and the scalar multiplication between these vectors and the scalars, they are potentially a little different from each other, but of course there's nothing wrong with letting those things be the same. So there are some linear operators that you actually are already familiar with, especially if you took single variable calculus. So the first linear operator that I want to discuss is derivatives. So derivatives are linear operators. And what do we exactly mean by derivatives are linear operators? That is, if I take constants a and b and differentiable functions f and g, then I can, in a sense, distribute derivatives over sums and factor out my scalars outside of my differential operator. In particular, I can write this instead as a times the derivative of f of x plus b times the derivative of g of x. And some people will even write that as a times f prime of x plus b times g prime of x. Now, how would someone prove that this identity indeed holds? If you know anything about derivatives, you probably know the limit definition of derivatives. And if f and g are differentiable, then you should be able to prove that with no issue. Instead of proving it, I just want to give a quick example, since this is not really a single variable calculus discussion, and sort of illustrate why the linear operator property is important for derivatives. So for example, let us assume we want to find the derivative of 3 times the sine of 4x minus 7 times e to the power of minus 2x. So since this derivative operator is linear, it can distribute over these two terms, and these constants can sort of factor out outside of the derivative operator. So that means this is going to become 3 times the derivative of this differentiable function sine of 4x minus 7 times the derivative of this differentiable exponential function e to the minus 2x. And then using whatever rules you have at your fingertips, you should be able to tell me what these derivatives are, and that's pretty much what single variable calculus is dedicated to. In particular, you should be able to show that this is going to be equal to 12 times the cosine of 4x, and this is going to be equal to positive 14 e to the minus 2x, and that is the derivative of the original function. But in order for us to take the derivatives of the individual pieces, this derivative operator needs to be a linear operator. Another linear operator that you should be able to be familiar with, again, if you took single variable calculus, is integrals. So integrals are linear operators. All right? In particular, one can prove that the integral, the definite integral, moreover, from a to b, let's say c1 times f of x plus c2 g of x, integrating, of course, with respect to x. Let's assume c1 and c2 are real numbers and f and g are both integrable functions. Then one should be able to show that this is the same as c1 times the integral from a to b of f of x dx plus c2 times the integral from a to b of g of x dx. And then using the fundamental theorem of calculus, you should be able to show that that's just the same as c1 times capital F of b minus capital F of a plus c2 times capital G of b minus capital G of a, where capital F and capital G are the antiderivatives of little f and little g, respectively, i.e. the derivative of capital F is equal to little f, and the derivative of capital G is equal to little g. And in case you're interested in knowing how to prove this, you can prove this via the perspective of, say, Riemann sums, if you're familiar with that from single variable calculus. But if not, we can just take this as fact, just to illustrate what's going on here. So let's just do a quick example and see why the linear property of integrals is very, very useful. Let's assume that we want to take the integral from 1 to 2 of the integrable function 3 over x plus 5x squared. So since definite integrals are linear operators, we can distribute over these two terms, and we can also factor out these constants outside of our integral. Once we perform that operation, i.e. take advantage of the linear operator property, we have this is going to be equal to 3 times the integral from 1 to 2 of 1 over x dx plus 5 times the integral from 1 to 2 of x squared dx. And from here, then the single variable calculus comes into play. You need to know what the integral of 1 over x is, and you need to know what the integral of x squared is, and then we can apply the fundamental theorem of calculus. So we should know that the antiderivative of 1 over x is just going to be equal to the natural log of the absolute value of x, and then we need to take the limit as x approaches 2, as x approaches 1, and then subtract. And then we have 5 times the antiderivative of x squared, which you should know to be 1/3 x cubed, for which we need to take the limit as x approaches 2 and as x approaches 1 and subtract. So this first term is going to be equal to what? So we're going to have the natural log of the absolute value of 2, which is 2, and the natural log of the absolute value of 1, which is 1. And then we have 5/3. We can multiply those constants together with no big deal. And then we're going to have 2 cubed, which is going to be equal to 8. And then 1 cubed, which is going to be equal to 1. So over here we have 3 times the natural log of 2, because the natural log of 1 is just going to be equal to 0. And then we have 5/3 times 8 minus 1, and 8 minus 1 is just going to be equal to 7. True? So I guess that can be your simplified answer if you really want it to be, but I'm just going to bring my 2 up into the power of 2, so we're going to have the natural log of 2 cubed, which is going to be equal to 8, and then 7 times 5 is 35/3 as my final and simplified answer, right? But we achieved that via the properties of the linear operator property of definite integrals. Now, an example of a linear operator that does not belong, at least on the surface, to single variable calculus is m by n matrices. So all m by n matrices are linear operators. In particular, they are linear operators from vector space Rn into vector space Rm. Let's give a quick proof of this. So, proof. Since we're in a linear algebra context, a proof of this is not asking for too much. So what we're going to do is we're going to let x and y both belong to Rm. We're going to let a and b both belong to the scalar field of R, and we're going to let A be an m by n matrix. So what do we have here? So we're going to have A times the vector ax plus by, right? And keep in mind this object belongs to Rn. And why is that the case? Well, we already know how to define scalar multiplication in Rm, so we know that those are defined. And we know if we take an Rn vector plus an Rn vector, we get another Rn vector. So we're applying a m by n matrix to a n row by one column vector, and that should give us some object, right? So if we look at this a little bit more detailed, we should know that this can be decomposed by distributing those over those things by properties of dot products. So we see that that's just going to be equal to AAX plus ABY, right? And again, that's by properties of dot products. Because matrix multiplication is just dot products in disguise, right? Because that is just the dot product of the column values with each of the rows. No big deal there. Or the row transpose, I guess you could say. And then we can rewrite this as A times AX plus B times AY, and that's by properties of scalar multiplication. So I'm just going to put a little quote proof because there's some details that you might be able to have here. So keep in mind that if X is belonging to Rn and A is an m by n matrix, that belongs to Rm, that belongs to Rm. Scalar multiplication of Rm is also Rm, and that's also going to be an Rm vector. So if you can put all the little details there of why those things are the case, then you have a proof that all matrices are indeed linear operators. So that's going to be very, very useful for us. Some very special types of matrices that are, again, linear transformations are rotation matrices, not just in R2, but of Rn as well. So let's consider two scenarios. The first, let's assume that we first have the vector 1, 0, and we desire to rotate this vector counterclockwise, and we want to obtain that vector. Let's assume that that is angle theta. Via the properties of trigonometry, that is of course going to be a right angle, and you should be able to verify that this vector here on the hypotenuse is going to be the vector cosine theta and sine theta. In addition, let's assume that we also want to rotate the vector 0, 1, and in particular we want to rotate it again counterclockwise by some angle theta. You should be able to verify via the properties of trigonometry that this vector is the vector minus sine theta, cosine theta. So is there a matrix that we can apply to any vector in R2 that will give us the rotated vector counterclockwise by theta degrees, or theta radians? So what we see here is R theta, which is going to be a matrix of the form A, B, C, and D, and we need to multiply, for example, this matrix times some vector x in R2, and we're going to get another vector y also in R2 that is rotated counterclockwise by theta, right? So rotate counterclockwise by theta, and no other transformation, of course. So via these two equations, because if we rotate 1, 0, we get 0, 1. If we rotate 1, 0, we get cosine theta, sine theta. If we rotate 0, 1, we get minus sine theta, cosine theta. So we have a systems of equations from that. In particular, we have that A, B, C, D times 1, 0 is going to be equal to cosine theta, sine theta. And we also have that A, B, C, D times 0, 1 is going to be equal to minus sine theta, cosine theta. So we have a systems of 4 equations and 4 unknowns, A, B, C, D, and you should be able to solve those equations for A, B, C, D, and you should be able to show that R theta, which is going to be equal to A, B, C, D, actually is equal to cosine theta, sine theta, minus sine theta, and cosine theta, right? A very important property, or maybe on the surface important, is that the determinant of R theta, the determinant of this 2 by 2 rotation matrix, is going to be equal to what? So it's a 2 by 2, so the determinant is not that difficult, but it's going to be cosine theta plus sine squared theta And we know that regardless of the value of theta, that's always going to be equal to 1. Also, if we take the vector cosine theta, sine theta, and dot product that with the other column, minus sine theta, cosine theta, notice that we get cosine theta, negative sine theta, plus sine theta, cosine theta, and those are just product opposites, so that's going to be equal to 0. So since the determinant is equal to 1, also we can take the norm of each of those vectors. For example, the norm of cosine theta, sine theta, and also the norm of minus sine theta, cosine theta, they're both going to be the same. They're both going to be equal to 1. So by these two properties, and this of course is a corollary, we see that our theta is an orthonormal matrix. And of course, since matrices are linear operators, we of course know that orthonormal matrices are also linear operators as well. Now, let's assume that we want to rotate a vector clockwise. So let's assume that we have our theta, and let's assume we have that direction. So this is a clockwise rotation. So this can be viewed, I guess, as the inverse of the other one. So this is the inverse of that particular matrix. So the inverse of clockwise would be counterclockwise. So that's just going to be equal to what? So it's going to be equal to cosine minus theta and sine minus theta, and then minus sine minus theta, and then cosine minus theta. By the parity identities of sine and cosine, we should know that cosine minus theta is cosine theta, sine of minus theta is sine of theta, and then minus sine theta is just going to be equal to sine of theta. I don't need parentheses here, that's overkill. And the cosine of minus theta is just going to be cosine theta. Right? And you should be able to verify that that indeed is the inverse of the original matrix as desired. So there are a couple other matrices that do transformations in R2. For example, Rx, which is going to be equal to 1, 0, 0, 1, Ry, negative 1, 0, 0, 1, and Ro, which is going to be negative 1, 0, 0, minus 1. I want you to take a moment and see what happens when you apply these vectors to some vector in R2 and what the resulting vector gets, and describe what each of these particular matrices do. Right? So another type of transformation, because you should be able to verify that these are each reflection matrices over the x, over the y, and over the origin line. Another transformation that you may want to consider is, suppose we want to stretch or compress a vector. So let's draw a little picture here. So let's assume that we have a vector u, and we want to have another vector there. So notice that this corresponds to x, this corresponds to y, and now y goes up here, so let's call that kyy, and x goes out here, let's call that kxx, where ky and kx are scalars. So this new vector is going to be equal to kxx and kyy, where kx and ky are scalars. You should be able to show that this particular transformation, which I'm going to represent by S for stretch, is going to be the matrix Kx00, Ky. Right? So let's look at an example where we might want to combine all of these at once. So let's assume we have U, which of course belongs to R2, be equal to the vector 3 minus 4. Now let's assume that we want to perform the following transformations. In particular, let's assume that we want to flip it about the x-axis first. And the second thing we want to do is rotate counterclockwise by 60 degrees, which is the same as pi over 3 radians, in case you don't know. Then I want to stretch horizontally by a factor of 3. And then 4, I want to stretch vertically by a factor of 0.5. in some sense, I'm compressing it by a factor of 2. I guess you could say it. And let's assume we want to do it in this order. So if we write this in matrix notation, then we have a vector u. First, we're going to be flipping it across the x-axis. Then we're going to be rotating that by some angle theta. And then we're going to be stretching that resulting vector. And that's going to be our resulting vector. And keep in mind, notice that it goes in that direction in terms of order. And notice that I'm combining the horizontal and vertical stretch in the same exact matrix. So if I write down these matrices explicitly, then I have what? So I have my lonely vector, 3 minus 4. First, I'm going to be flipping it across the x-axis, so that's going to be equal to 1, 0, 0, minus 1. And then we're going to be rotating it. So cosine of pi over 3, sine of pi over 3, minus sine of pi over 3, and cosine pi over 3. And then we're going to be stretching it by the stated factors. So 3, 0, 0, 0, 0.5. Right? So you can, of course, multiply those matrices first, and let's assume we call that transformation t. One should be able to show that t is approximately equal to 1.5, 2.6, 0.4, negative 0.3. So this matrix T does those things. So once you have T, then TU is going to be equal to approximately 1.5, 2.6, 0.4, and negative 0.3 times 3 minus 4, and that's going to be approximately equal to the vector negative 5.9 and 2.3, and that's the resulting vector after you apply each of these transformations. Before I close out with the last example of a nonlinear operator, I just want to give a couple definitions of terminology that is often used with linear operators. So let's assume that, for example, f is indeed a linear operator, i.e. it transforms this vector in some space S and turns it into this other vector of that particular structure in the space T. Then sometimes f is also called a homomorphism from S to T. Now, if f is bijective, in particular if f is 1-to-1 and also onto, in some sense f is invertible and you know practically everything about the range or the images of the elements in S, then f is called an isomorphism from S to F, and S and T are said to be called isomorphic sets. There's a very important theorem about isomorphisms and isomorphic sets, and that's the following. So if S and T are isomorphic to one another, i.e. there exists an isomorphism from S to T, and hence there exists an isomorphism from T to S as well, and we call that the inverse linear transformation of F, then the dimension of S is equal to the dimension of T, where, of course, those are the typical definitions of dimensions from example vector spaces. Now, I'm not going to get into the applications of it here because this dives into more advanced ideas, but of course you can explore the ideas and the applications thereof in case you're interested. So let's give an example of a mapping that is not a linear transformation. So example, let's consider xy, the Cartesian point, belonging to the Cartesian product of R and R. And let's define the function from R cross R into R by the mapping fxy is equal to xy squared, where that's the typical multiplication and exponentiation by 2. So let's see if it satisfies the properties of a linear operator. So what is f of cx? So here x is going to be an object in R cross R. So we want to verify, is this equal to c times f of x? Right? So let's define this scalar multiplication. So let's define cx as we typically would in, say, R2. We're going to call this the point cxcy. right? So if that's the case, that means that fcx is going to be equal to fcxcy by definition, and that's going to be equal to cx times cy squared by the definition of the mapping F. So that's just going to be equal to cx c squared y squared by properties of exponents, and that's going to be equal to c cubed times xy squared. I'm going to decompose this slightly. I'm going to write this as c squared times cxy squared, because this particular thing is the definition of c times fxy. And we know that fcx must be equal to c times fx if this is indeed a linear operator. But notice that this is not true for all c, right? For example, c could be equal to 2 and it's not equal to each other. But in this particular case, if c is equal to plus or minus 1, it would hold, but that's not for all c. So it's not always true. And hence this is not a linear operator, and hence some people call it a nonlinear operator, and there's plenty of theory for that. So those are just some of the basics associated to linear operators and linear transformations. For a more in-depth exploration, that would probably be more appropriate for, say, a functional analysis discussion, which we'll definitely have in the near future. So I hope you enjoyed, and I'll see you in the next video. Take care.